Hi everyone, in this video we can discuss about elliptic curves over Galois field with set of numbers in the form 2 to the power m. That means we are considering here binary numbers, okay, because the base is 2 here. And this Galois field we can call it as finite field also, okay. And for a set of numbers to be a finite field, we need to consider two more binary operation along with set of numbers, that is that plus operation, addition operation and multiplication operation. And that set of numbers with that addition and multiplication operations satisfying all these conditions, we can say that that set is a finite field. And the first five properties A1 to A5, these are defined for addition, and the rest M1 to M7, they are defined for this multiplication operation. And for any set that satisfying all these conditions over addition and multiplication, we can call it as a finite field. Here we are going to define that elliptic curve points over this Galois field. We have already seen one equation for this elliptic curve over real numbers, that is y square equal to x square plus ax plus b. Here we need a modified formula equation for our elliptic curve over this Galois field, which is y square plus xy equal to x cube plus ax square plus b. This is the modified equation for elliptic curve over finite field of 2 to the power m. And here it is defined two tables, one for addition operation over this Galois field with values 2 to the power 3. That means all the binary numbers that can be represented using 3 bits. That is the number set. We need to consider the Galois field that is defined over 3-bit binary numbers. So the numbers are 000 to 111. Okay. So here the first table indicate addition table, from second table indicate multiplication table. From this the third table is derived. That first column indicate that addition inverse and this is multiplication inverse. So consider this case. For A, the addition inverse is C. If it is 0, the addition inverse is 0 itself. 1 itself. For 2, the addition inverse is 2 itself, and so on. Okay, and this is not the case in case of multiplication operation, and these values are derived based on this table. Okay, so for adding 0 with 0, we get a result 0. That is the additive identity. So from this we need to remember this particular point, that additive inverse of a number is that number itself in case of this operation, addition operation defined over Galois field of 2 to the power 3. Okay, the additive inverse is the number itself. Okay, keep this point in your mind. And for this multiplication inverse, we can say like that multiplication inverse of a number is the number itself. This is not valid for multiplication, this is valid for addition only. Okay, and this is clear from this table. While adding that number with the same number, we get additive identity as the result, so that we can say that number is the additive inverse of the same number. Okay, and here we have performed certain operation which is not the conventional method of addition and multiplication. For defining this addition and multiplication over this Galois field of 2 to the power 3, we need to consider modular polynomial arithmetic. Okay, consider an 8-bit random binary pattern. How can we convert this into polynomial form? In order to perform this addition and multiplication operation, we need to convert this number into polynomial form. For that, we need to write all the powers of x in sequence, starting from LSB position, x to the power 0, x to the power 1, x square, x cube, etc. And here it is 1 into x to the power 7. Okay, so we need this term in our result. Discard this 0 multiplication, 0 product, we can discard this. Again 1 into x to the power 4, we need this term in our result. Discard this. This is 1 into x square. Discard this. Then 1 into x to the power 0. X to the power 0 is actually 1. So 1 into 1, 1. So this is the polynomial representation corresponding to this binary pattern. And here also, discard this term. 1 into x to the power 6, we need this term in our result. 1 into x to the power 5, we need here in our result. Discard this. And x cube in our result. Discard this. 1 into x to the power 1 in our result. Discard this. And this is our result. Okay, then consider one other example. 0, 0, 0, we can write it as 0 in polynomial form. 0, 0, 1 is 1 itself. 0, 1 x is, this is case x to the power 0, x to the power 1, x square. So this is equivalent to 1 into x to the power 1, that is x itself. Then here x to the power 0, x to the power 1, x square. So discard this 0 multiplication. Then x to the power 1 into x to the power 1 plus x to the power 0, that is x plus 1. So we can write the polynomial equivalent of any of the binary pattern. And we need to consider one more case, that is, if while we are performing certain polynomial multiplication, sometimes our product exceeds, that order of our product exceeds this Galois field order. That means after multiplication, sometimes we get a result like x to the power 4, x cube and so on. That means the resultant value exceeds, the resultant polynomial order or degree exceeds our Galois field. In that case, we need to perform an additional division operation, or we need to perform a modulo operation after this normal multiplication. And for performing this modulo operation, we need an irreducible polynomial. How can we get an irreducible polynomial? That irreducible polynomial should have that degree of this field. Here it is 3. So we can get a polynomial with degree 3. Okay, so here one example for such a irreducible polynomial, that is x cube plus x plus 1. Here the degree of this polynomial is 3, which is equivalent to the order of our Galois field. Okay, so this is the polynomial conversion corresponding to binary number. Now we can consider an addition and multiplication over operation using this polynomials. Suppose f of x is x square plus x plus 1, g of x is x square plus 1. Here m of x is actually that irreducible polynomial. We can make use it in case of multiplication operation. If the resultant product exceeds our Galois field order, then we need to perform further modulo operation using this irreducible polynomial. So for addition, here it is f of x plus g of x. For performing this addition, we need to remember this particular case, that is, that number itself is the additive inverse of that number. Okay, so performing addition, x square plus x square. Here in f of x and g of x, here is x square, here also x square exists. So these two are additive inverse of each other. So they, after addition, the result will be 0. That means they will cancel each other. Next is x. Here we don't have that further x here. That means there exists no additive inverse of this x here. So we need this x in our result. And for this one is here, one is here also. That means one is the additive inverse of other. So the result will be 0. So this is the final result of our addition. of these two polynomials. And what about this multiplication? After performing this multiplication, here it is the result, x to the power 4. Just perform x square into x square plus s square into x plus x square into 1. After that 1 into x square plus 1 into x plus 1. So after rearranging this, we get a polynomial like this. This is already exceeded our Galois field order. So for getting the exact result, we need to perform modulo operation over this polynomial. How to perform? X raised to 4 plus x cube plus x plus 1 is divided by that irreducible polynomial given here, that is x cube plus x plus 1. So while dividing this, first using this x into x cube is x raised to 4, x into x is x square, x into 1 is x. So consider these two. These are additive inverse, so cancel each other. Write this x cube here, write this x square here, and this x and x inverse each other, cancel this, then write this 1. Then next put a 1 here. 1 into x cube is x cube, 1 into x is x, 1 into 1 is 1. Then this cancel each other, then x square x, and again it cancel each other. Then our multiplication result is x square plus x. Okay, so based on this multiplication and addition operation, these tables are defined here. Okay, and from this it is clear that additive, what are the additive inverse? The number itself form the additive inverse of the number. And for the multiplication inverse, for 1 is the multiplication inverse, 2, 5 is the multiplication inverse, 3, 6 is the multiplication inverse, and so on. Okay, so these are that addition and multiplication operation based on polynomial arithmetics. So here one example is given. Consider a Galois field with 2 to the power 4. That means we need to consider all the binary numbers with 4-bit representation, all the possible 4-bit representation of binary numbers. Okay, then here it is given that irreducible polynomial is f of x equal to x to the power 4 plus x plus 1. Thus order and the degree of this irreducible polynomial should be the same. Then we have an additional generator polynomial, that is g to the power 4 is given as g plus 1. Okay, so g plus 1 means binary in a, this is in polynomial form, its binary is 0, 0, 1, 0. Okay, g means 0, 0, 1, 0. We can consider, here it is 4-bit representation. So g to the power 0 can be represented as 0, 0, 0, 1. G to the power 1 is 0, 0, 1, 0. G square is 0, 1, 0, 0. G cube is 1, 0, 0, 0. And after that g4 is given as g plus 1. Okay, so we can write this g4 directly from this given information. This is 0, 0, 1, 1. And g power 5, how to calculate g to the power 5? G to the power 5 is actually g to the power 4 into g. What is that? G to the power 4? G to the power 4 is g plus 1 into g. We can perform this operation, that is g square plus 1. What is g square? That is 0, 1, 0, 0 plus 1. Okay. So consider this operation, g to the power 4 into g, g plus 1 into g, that is g square plus g. Sorry, not g square plus 1, this is g square plus g. Okay, g square plus g is what? From this, we know that what is g square? 0, 1, 0, 0. This is actually g square plus g, not g square plus 1. Okay, so we know that g square is 0, 1, 0, 0 and g is actually 0, 0, 1, 0. Here we can perform, in order to perform this addition operation, we can perform XOR operation also. Okay, Here XOR operation is equivalent to addition. 0, this is 1, 1, 0, 0, 1, 1, 0. So 0 is to 5 is, we can calculate g to the power 6. We can either go for g to the power 5 into g or g to the power 4 into g square. Okay, g to the power 5 into, we have already defined this g to the power 5. What is this g to the power 5? G to the power 5 is actually g square plus g. So this is into g. We can write it as g cube plus g square. Okay, what is g cube? G cube is 1 0 0 0 and g square is 0 1 0 0. So perform this XOR operation, then we get 1 1 0 0. So based on this, we can define all this g to the power 15 values, and note, consider this one g0 and g15. These two are with same representation, so that 0 0 0 0 combination is missed here. So we can consider this as that 0. Okay, so based on that, we can plot a graph like this from 1 to g to the power 15. Instead of 15, we can write it as 0. Again, along y-axis 1 to g to the power 15. Okay, then here consider that modified equation, and one example is given here with a with g to the power 4, b with g to the power 0, that is 1. Then substitute this a and b value over this modified elliptic curve equation. Then we get a formula like this: y square plus xy equal to x cube plus a is g to the power 4. G to the power 4 into x square plus 1 into 1. Okay, so this is the formula. And consider one pair, x with g to the power 5 and y with g to the power 3, and substituting this xy value over this modified elliptic curve equation, we get that both LHS and RHS with same value. That means these particular points satisfying this modified elliptic curve points. That means this point comes under this elliptic curve. And similarly, we need to consider all the combination 1 1, g1, g square 1, g cube 1 and so on. Similarly, g1, gg, gg square, gg cube, and all the possible pairs, and substitute all the possible pairs over this elliptic curve equation, and identify all the pairs that satisfying this formula. And these are all that set of pairs that satisfying this particular modified elliptic curve formula, and plot these values over here. Now this is the derived graph based on this elliptic curve points. Now we can define rules of addition over this elliptic curve over our Galois field with given a and b coefficient values. First point is p plus o is p. This o is actually what? That additive identity. Adding the additive identity with any particular elliptic curve point, the result will be the number itself. And consider this p a point and another point with xp comma xp plus yp. Adding p with that point at xp comma xp plus yp point, it will generate result as that additive identity. That means this is the point, that is the additive inverse of this given p, that is minus p. P plus minus p is that additive inverse 0. Is this valid? If we know p, is it valid, or is it possible to get this minus p at this coordinate position xp or xp comma xp plus yp? Consider this case. Consider a point in this graph p with g3 comma g8, x with g3, y with g8. This is the point. This is that point, this one. G3 and G8. And where is its minus P? Minus P is here it is. With x coordinate of these 2 points are the same, that is G3 itself. And y coordinate is what? X plus y point. Okay, that is G3 plus G8. G3 plus G8. Is it G3 plus G8 equal to G30? For performing this addition, we need to consider the representation of G3 and G8. We need to perform XOR operation. G3 is from this derived table. We know that G3 is 1000 and G8 is 0101. Okay, so in order to perform that addition, just perform that XOR operation. We will get 1101. 1101 is actually what? 1101 is G13. Okay, so we get that additive inverse in this particular point G3, G30. Okay, so this is the coordinate position of a additive inverse of a given number P. If P with coordinate xp, yp, its additive inverse will be at point xp, xp plus yp. Okay, and similarly, if two different points are given like P and Q, P with xp, yp, Q with coordinate xq, yq, and here we have defined formulas for getting the sum coordinate. P plus Q equal to R, the coordinate of R will be XR and YR. This is the formula for getting XR and this is the formula for getting YR. The sum value coordinate of our sum. XR is lambda square plus lambda plus xp plus xq plus A. This lambda means the slope. And the equation for getting the slope in this case is yq plus yp divided by xq plus xp. And A and B are the coefficients of given coefficient value of our elliptic curve equation. And for YR it is lambda into xp plus xr, xp plus xr plus xr plus yp. Okay, so these are the defined rules of over elliptic curve or elliptical points defined over Galois field. And one more point is, if a point P is given with coordinate xp, yp, we can calculate the double point after doubling operation, that is r equal to 2p, coordinate is represented as xr, yr. This is the formula for getting xr and yr. Xr equal to lambda square plus lambda plus a, yr equal to xp square plus lambda plus 1 into xr, where lambda is the slope again, and the modified equation for slope is xp plus yp by xp. Okay, and these are the rules for addition over elliptic curve points defined over this Galois field. Okay, thank you.